done a lot of awesome foundational work on Log-Concave sampling over the years, and it's our pleasure to have him. So go ahead, Arnak.
Thank you very much. I would like to start by thanking the organizers for this very nice workshop. Unfortunately, I couldn't go to Berkeley for being present in person, but having the opportunity to give a talk via Zoom is a good thing as well. So it's already evening in Paris, so I might be a little bit tired. But in any case, if you have any question, please do not hesitate to interrupt me during my talk and to ask the question. So the paper that I will present now is about Langevin Monte Carlo for log-concave densities. The important point here is that there is no the word strong in the title, so we will be mainly focusing on the case where the density is log-concave, but it's not log strongly concave. It's a joint work with my former PhD student, Avetik Karagulyan and Lionel Riou-Durand. So let me start very slowly by introducing the framework. So the goal is something which is, I think, very clear for everyone in this audience, is to sample from a probability density function, which will be denoted by pi theta. And it can be written via a potential function, which will be denoted by f. So we will assume that the potential function is defined on the whole space R to power p. And we will also assume that this function is convex. We will not assume strong convexity on f, but in order to have some control on the flatness of f, we will assume some bounded moment assumptions, and more precisely, we will denote by mu subscript q the moment of order q of the distribution pi, and we will assume that it's finite for q equal to 2. And we will also need to have some smoothness assumptions on f. The most natural smoothness assumption here is just to assume that the function f is gradient Lipschitz. So it's just written here, the gradient of f should be Lipschitz. And I've already said the function f has to be convex, which means that, if the second order derivative of or the Hessian matrix exists, then it should be definite positive. There are many, many natural examples appearing in statistics which satisfy these assumptions. And the simplest one is probably the multivariate logistic regression. One can easily check that if one is in a multi-dimensional setting, the logistic regression, if one uses the Bayesian approach and defines the posterior distribution function, it will be log-concave, but it will not necessarily be log-strongly concave. So what is the goal in this work and in this talk? So the goal is just to find the distribution nu such that it is easy to sample from nu, and we have some guarantees indicating that the Wasserstein distance between nu and pi is small. Let me just do two very small remarks here. First of all, we can have a very naive sampler with just samples 0 at each iteration, and constantly 0. In this case, it is clear that the Wasserstein distance between the sampler and the target will be bounded from above by this quantity mu of q. And I will go back to this point in a few slides, but the goal that we will have here is to try to do so that we get an accuracy which is epsilon times the accuracy of this naive sampler. And an interesting feature of the log-concave densities, there are many interesting features for log-concave densities, but one particular feature, which is also very useful in the context of sampling, is that all the moments are equivalent. In other words, there are some constants AQ. Of course, they depend on Q, but they do not depend on the probability distribution pi, such that the So the moment of order q is upper bounded by this constant aq multiplied by the second order moment of pi. Okay. So for instance, this inequality was known long ago. We can so it can be proved using a very famous Borel inequality, but we did a little bit tedious work in order to figure out what is the real order of magnitude of the constants involved in this inequality, and it turned out that, just curiosity, for q equal to 3, q is smaller than 3.5. For q equal to 4, it's 4.6. And we have a complicated formula involving the incomplete gamma function, which allows us to compute these values for every q. So it's a small contribution of our paper. I wanted to mention it right away, but it's just a small curious fact. Now, what we will be studying in this paper and in this talk are MCMC methods, which are based on the evaluation of the gradient of the potential function. So I will refer to these methods as first order MCMC methods, doing the parallel with first order optimization. And perhaps the most natural candidate for approximating the distribution pi here is the Langevin Monte Carlo method. So the definition of the Langevin Monte Carlo, I guess, has been already given during yesterday's talk, and most of people present in the audience know this definition. Here I just wrote the definition in order to show notations that I will be using throughout this talk. So theta k will be the state of the MCMC process that I will be studying. H usually will denote the step size, so it will be a small parameter. K will be the number of iterations, and Xi will denote the innovations, the random innovations that we are adding to the gradient descent in order to make it stochastic and to make it converge to a distribution instead of converging to the single point, which is the minimizer of f. Okay, so here for the Langevin Monte Carlo, the innovations are IID, Gaussian with zero mean, and identity covariance matrix. And also I will denote by nu the distribution of different Monte Carlo algorithms. So nu subscript k will mean that it's the MCMC iterated k times, and as the superscript, usually I will try to write the name of the algorithm. Okay. So this is the standard LMC. It will be one of the candidates we will be studying. The second interesting candidate is the Langevin Monte Carlo with averaging. It's a very simple one and can be seen as a particular case of the LMC. What one has to do is simply draw a random variable tau, which is uniform between 1 and k, so uniform on this discrete set. And then once this tau is computed, we just compute the LMC up to time tau. Okay, so the average LMC will be just a randomly chosen iterate of the LMC algorithm. So why do we call this algorithm averaging or average Langevin Monte Carlo? It's simply because if you look at the distribution of this algorithm, so at the distribution of theta k a LMC, you can see that it's equal to the arithmetic mean of nu1, nu2 up to nu k, where nu k is the distribution of the original LMC. A third algorithm that is studied in this framework is the so-called kinetic Langevin Monte Carlo, which is also known as underdumped Langevin Monte Carlo. So the complicated formula is written here. It's not very important to understand, to parse this formula. The important point is that the iteration k plus 1 is defined as a mean which involves the gradient of f plus a Gaussian vector. And these Gaussian vectors are also IID, and one has to write the covariance matrix of these Gaussian vectors. I didn't write it here because it's a little bit complicated, but there is a precise form for this covariance matrix as well. And of course, for all the methods which are written here, we can also use the Metropolis-Hastings adjustment of these methods. In this talk, I will only focus on the case of the LMC, so the Metropolis-Hastings adjustment of the LMC, which is called in the literature MALA, so MALA. Okay, so what these different kind of MCMC are doing, if we draw the picture in the one-dimensional case, we can surround different paths of this Markov chains and go up to time, say, 30 to see where they arrive. And if we see the positions of the particles up to time t, and we draw the histogram of these positions, we can see that these histograms are close to a probability density function. And here, this probability density function will be equal to the target density pi. So the main goal that we have here is to evaluate the number of gradient evaluations which are sufficient for getting an epsilon accuracy. Of course, we want to understand how this number depends on epsilon, but also how this number depends on the dimension and how this number depends on the condition number. I will go back a little bit later to what the condition number is. It's not, it's easier to understand in the case of strongly log-concave densities. It's a bit more trickier for densities which are log-concave but not strongly log-concave. So the important quantity that we are trying to control here is the mixing time. So if we have a given algorithm and we use the Wasserstein distance WQ, then the mixing time will be defined as a smaller integer, such that if we do k iterations of the algorithm, then we will get a probability density function which distance to pi is smaller than epsilon times the moment of order q of pi. So this quantity will be the main quantity of interest in this work. And let me start now. Let me give now a quick overview of the results before going to the details. As I have already told, we want to understand the order of magnitude of this k, the mixing time. And this table here describes very quickly how this quantity k depends on dimension p, the precision epsilon, and the condition number kappa. And you can see on the top left corner of the table here, the definition of the condition number kappa. So we define it as the Lipschitz constant m multiplied by the second order moment squared divided by dimension. So this definition is convenient for several reasons. First of all, if we use this definition, then kappa is invariant by scale change. So if instead of sampling from pi, we want to sample from a distribution which is just obtained from pi by a change of scale, then this kappa will be exactly the same. So it will not change. And the second reason for using this kappa is that in the strongly log-concave situation, one can check that mu2 squared is equal to the dimension divided by the strong convexity constant. Okay, so if we replace mu2 squared by p divided by strong convexity constant, we obtain here capital M divided by say small m, which is the strong convexity constant, and this is exactly the definition of the condition number in the strongly log-concave situation. Okay, so just keep in mind that we are using this definition of kappa, and with this definition of kappa, which was already done in the literature, is bound on the total variation distance. So these results are written on the bottom line of the table. The first row is the result for the Langevin Monte Carlo with averaging. This result has been obtained in a very nice paper by Geometries, Majewski, and Miasoyedov. And it has a very nice dependence on dimension and on the accuracy, so on epsilon. And also a very nice point in this result of this first column is that the numerical constants are given explicitly and they are really reasonably small. So this is an important point for me because basically when I started to work on MCMCs, the main reason for me to get interested in it was that some of the students came to me and said, okay, I have an MCMC algorithm. I want to approach some density and I don't know how many steps should I perform in order to attain given epsilon accuracy. And so the student was often asking me whether there is a theoretical way of defining the number of iterations. Of course, it is closely related to the convergence diagnosis of MCMC algorithm. And when I really looked through the literature, I saw, and it was a little bit surprise for me, that there were almost no results that could be used even in the simplest situation. Even for getting some numbers which are very, very high, it was not really possible to get results. And we know by now that in the strongly log-concave situation, we can have such results. And the goal of this paper is also to get such results for log-concave situations in which we have explicit constants everywhere and nice dependence on different parameters. So for the LMCA, there is this result for the total variation distance. For Mala, there is this second column, which is derived from the paper by Dwivedi et al. And I should mention here that the speed is very good, especially dependence on epsilon is very good, better than all the others. But this result comes without explicit constants, and if we try to obtain constants there, they are really very large. And finally, the two last columns of the table, the first two rows are the results that we obtain in our paper, and the results of the last row and the third column was in my original paper of 2017 on the Langevin Monte Carlo for strongly log-concave distributions. Okay, I will come back to this table a little bit later on to compare different results. Let me move forward now. So in order to handle the case of log-concave distributions which are not strongly log-concave, I will present here three main approaches one could think of, and I will try to compare to say which are the weak and strong points for each of these approaches. Are there any questions so far? No. Okay, so I can continue. First of all, there is a very simple proposition which is simple to prove. So I gave a sketch of the proof here, but let us just read the statement of the proposition. It tells us that if we are interested in the Wasserstein distance of order q for any q which is larger than 1, we can bound this Wasserstein distance using any bound on the total variation distance. Okay? So we simply need to bound the total variation and moments of the distributions mu and mu prime of order r, where r should be larger than q. Basically, the best bound is obtained when r tends to infinity, because then the power of total variation distance becomes the largest, 1 over q. But then the constant which is in front, which corresponds to moment of order R, explodes because these moments usually go to the infinity. So there is the proof, the idea of proof here, but in the interest of time, I think that I will not spend time on that. Just let me mention here that if we use this inequality, in the case where one of these two distributions is log-concave, then of course, as I have already mentioned, the moment of order R can be upper bounded by the second order moment. And if we assume that the other distribution has a, say, for instance, first order moment, which is not larger than the second order moment of the target distribution, then we can relate the mixing time in Wasserstein 1 distance to the mixing time in total variation distance. And basically, it simply says that if we want this mixing time in W1 distance, we need to compute the mixing time of total variation distance, not at epsilon, but at epsilon divided by AR to this power, which is close to 1. Okay? And recall that AR was the constant which was involved in the comparison of moments for log-concave distributions. So usually AR goes to infinity when R goes to infinity. Okay, so we have these two results written here. The one for W1, the one for W2. And the important thing to notice is that for W1, we should have the total variation distance bounded by epsilon to power 1 plus something. For W2, it should be epsilon to power 2 plus something. Okay? So there is a power 2 popping up here. And if we use these results in combination of the last row of the table, so we can easily see that from the last row, which are bounds for the total variation distance, we can infer bounds for W1 and for W2. So the formulas which are written here in red are complicated, so I will not read the formulas, I will just quickly comment them. So what we see, for instance, compare the first, so the second row and second column, yeah, and assume that R is equal to infinity and forget about the factor AR to power 8. So what we get here is P squared over epsilon 8, which is worse than the P squared over epsilon 6 that we get by our method that I will describe later. For Mala, it's a little bit different. Once again, I have said that Mala behaves very well as a function of epsilon. So here we see this behavior. We have epsilon to power 3 instead of epsilon to power 6 or to power 5. But the dependence on P is worse. The dependence on dimension here is P to power 3. And once again, there is this constant AR to power 3, which pops up here, which also can be very large. Yeah, numerical constants also are not very good for Mala here. Okay, let me now talk about the second approach, which is based on Poincare inequality. So I recall here that a function, a density function pi satisfies the Poincare inequality if such an inequality is satisfied for every function h, which is locally Lipschitz and integrable, squared integrable. So what's important here is the constant Cp, which is in front of the integral here. And of course, we are interested in having distributions for which this constant Cp is as small as possible. A very nice fact about log-concave distributions is that any log-concave distribution satisfies the Poincare inequality, which basically means that Cp is finite for every log-concave pi. But what's less, what's a bit annoying here is that we know that this constant Cp is finite, but we don't really know what is the order of magnitude of Cp. Of course, there is this famous KLS conjecture, which, if it's true, it helps to understand the order of magnitude. But even in that case, we cannot really. There are no easy way to evaluate this constant Cp for a given distribution pi. So it's only so why this Poincare inequality and the Poincare constant is interesting in the framework of sampling, because the Poincare constant is exactly equal to the spectral gap of the transition operator, so to the inverse of the spectral gap of the transition operator. And therefore, there is an inequality which says that if we consider the distribution of the Langevin diffusion at time t, so let us call it nu subscript t, then the distance between nu t and the target distribution pi decreases exponentially fast. So the rate of the exponential decay is 1 over Cp. Okay, so here Cp is the Poincare constant. So using this kind of algorithm, there are several papers that establish the results for, using this kind of arguments, there are several papers that have established guarantees for sampling algorithms. Here I mentioned perhaps the most recent paper, which is a paper by Lehec, and there is this theorem 3 which says that if the target distribution pi is log-concave and the potential function f is Lipschitz with constant L, and be careful here, L is not the capital M, because I was using capital M for the Lipschitz constant of the gradient of f, but here only the function f is assumed Lipschitz. The gradient is simply assumed locally Lipschitz, and the constant doesn't matter there. So their result says that if the step size is reasonably small, then there is this bound here for the Wasserstein-2 distance. I'm sorry, there is a small typo here. This should be Wasserstein distance squared here. Okay? So the Wasserstein distance squared is upper bounded by this quantity. And we see that this upper bound contains explicitly the dependence on the step size h, on the number of iterations k, which is present in the both terms here. And also it involves the Lipschitz constant L and the Poincare constant P. And the chi-square divergence between the initial point mu0 and pi can be upper bounded as well in the case where the initial point is chosen as a Gaussian distribution with the center, the minimum point of the potential function. And
hi, Arnak, can you hear us?
Yeah.
So we're having some audio difficulties with the speaker. Do you mind giving us a few seconds to fix it? Okay,
No problem.
Thanks so much.
Check, 1, 2. Arnak, I think we're up and running again. If you want to continue.
Yeah, okay. So should I repeat some parts, or I can resume from the point where I was? Okay, I assume that I can just continue. So there is this result obtained by Joseph Lehec, and if we use this result and compute the mixing time, we get something which is proportional to the Poincare constant to the power 3 multiplied by L squared, dimension squared, divided by epsilon to power 4. So once again, if we compare with the table presented above, we see, for instance, the dependence on dimension is approximately the same. The dependence on epsilon is to power 4, so it's not better than what we have here. And the annoying thing is that there is this Poincare constant which pops up here, which might depend on P, and for which we don't have any good control as for now. And another annoying point is that the function f is assumed to be global Lipschitz, which might be violated in some situations. In a very simple case, if you assume a Gaussian distribution with degenerate covariance matrix, then the function is not globally Lipschitz. It's globally gradient Lipschitz, but it's not globally Lipschitz. Okay. So let us move to the third approach that we have used in our paper, and which is probably the simplest approach. It is based on the convexification trick. Just to explain it, let me mention that if the function f, if the potential function f is alpha strongly log-concave, then one can show that the Poincare constant is smaller than 1 over alpha. Okay, so one can replace in the exponential convergence the Poincare constant by 1 over alpha. And it is also known, for instance, it can be found in the book by Cédric Villani, that for the continuous time diffusion process, Langevin diffusion process, the distance between the distribution at time t and the target distribution pi satisfies this simple inequality here. So the goal and the idea of this third approach is just to add the quadratic penalty to the potential function so that this new potential function becomes strongly convex, and we can apply this kind of exponential inequalities to this penalized potential function. So we will denote the strength of the penalty by alpha. We will often call alpha the penalty parameter, and the new target distribution that we get using this penalized potential will be denoted by pi alpha. And a first result that we have established is that the distance between pi and pi alpha can be easily upper bounded as a function which goes to 0 when alpha goes to 0. For total variation distance, it is just upper bounded by a function which is linear in alpha. For the Wasserstein distance of order q, so the distance is upper bounded by alpha to power 1 over q. Okay, because here on the left-hand side, we have the power q of the Wasserstein distance. And we have also all the explicit constants in the inequalities for Wasserstein 1 distance equal to 22, for instance. Okay. From now on, when we talk about alpha LMC, it's simply this Langevin Monte Carlo method, which is applied not to the function f, but to the function f alpha, to the penalized potential. And how to analyze such a method? The basic tool of the analysis is just the triangle inequality, which says that if we compute the distance between the penalized Langevin Monte Carlo and the target distribution is smaller than the sum of these two distances, where for the first distance, it's just the quality or the precision of sampling from a strongly log-concave distribution. Okay, so this first distance here is something which has been thoroughly studied in the literature over past, say, 5 years, and there are many different results in different settings for bounding this term. And the second term is bounded in the proposition, which is just written above. So if we use this approach, and I give here, we can, of course, obtain plenty of results in many different settings under different conditions on F. And in the simplest result, which is about the alpha LMC, is the one written here, which says that this penalized LMC has an accuracy which is upper bounded by 3 terms. There is a first term which goes exponentially fast to 0. The second term is a discretization error, which is 0 when the step size h is equal to 0. And the third term is the term which is due to the penalty. So this term is 0 if there is no penalty, if alpha is equal to 0. So very often when I show this result, people ask me, why do we have alpha present in the second term? Second term accounts for the discretization error. And one could think that introducing this penalty alpha doesn't change the properties of the path of the diffusion process. So the discretization error shouldn't change. But the fact is that we compute here the discretization error after k steps. And so the number of steps we are executing here will depend on alpha. And since the number of steps depends on alpha, the discretization error depends itself on alpha here. Okay, so we have to divide here by alpha, and it's present also in all the remaining results. Anyway, we can use this upper bound for optimizing with respect to alpha and with respect to age. So first of all, we choose alpha so that this last term is small. And once alpha is fixed, we just minimize the sum of the first 2 terms with respect to age. And doing that, we get some simple upper bounds for the mixing time. For W1 distance and for W2 distances, these bounds are written here. And what we saw already in the table earlier were exactly these bounds without the constants and without the logarithms, just the simplified forms of these inequalities. There is exactly the same form of upper bound for the kinetic Langevin Monte Carlo, penalized by this quadratic penalty as well. Of course, here the situation is a bit harder from a technical point of view because there is this friction parameter gamma, which is also entering into the play. And we optimize with respect to all these parameters, alpha, gamma, and h. The upper bounds that we get have a better dependence on dimension, better dependence on epsilon, and the constants, numerical constants, are smaller as well. The only point where they are a bit worse than previous results is the dependence on the condition number. Unfortunately, the condition number here, which is this m times mu squared to power 3/2, is worse than the dependence for the previous result. And so I think that this is mainly due to the fact that for the K LMC, the results, the dependence of the existing results in the strongly convex situation are perhaps not optimal with respect to the condition number. Okay, so since I'm running out of time, let me conclude. So in this work, we analyze the situation of log-concave densities and how we can sample with some precise theoretical guarantees from these distributions in the case of gradient Lipschitz potentials. And we have shown that the simple convexification trick is still competitive with all the other natural approaches. But of course, the literature on this topic is very rich and it has grown very fast over past years. So it might very well happen that there are some results that I am not aware of. So if some of you in the audience have some result or can point to some results that I missed in this overview, I will be very happy. In our paper, we have also similar results under additional assumptions, and specifically in the case of Hessian-Lipschitz potential. And now we are working in improving these results by choosing variable step sizes hk and also variable penalty levels alpha k. And to the best of my knowledge, the discretization method which leads to the best results for LMC and for KLMC is the midpoint discretization introduced by Shen and Lee in their paper of 2019. So our goal is to combine these 3 points in order to get improved results. And the first step that we did in this direction was in a paper written with Aveti Karagulyan and published in Neurips last year, where we considered the continuous time process with variable penalty level alpha t, and we have proved that if we choose this alpha t as so morally inversely proportional to t, then the W2 distance becomes inversely proportional to square root of t. Okay. So we have these nice results for continuous time diffusion process. Now the goal is to discretize it, and we believe that using midpoint discretization, we will get the best results for this. So thank you very much. I would like just to finish with an announcement. I have a postdoc position in Paris. If some of you are interested in, or you have friends or students who are interested in, please feel free to send me an email. Thanks a lot.
Okay, cool. Oh yeah, thanks a lot, Arnak. And I guess we have time for a few questions before taking a break for the next speaker. Yes.
Hi, Arnak. This is ENSAE. Very nice talk. I just want to have one comment on the table for Mala. I think under your weekly Log-Concave case, the rate for Mala has been improved since DVD and all. Should I have p squared instead of p cubed? Then will be comparable with other algorithms. I can send you an email later to clarify. Yeah.
Yeah, thank you.
Any other questions? Oh, yes.
Yeah, hi, I have a question. Hi, Arnak. You say that under KLS and the Poincare constant could not be related to the to anything tractable, isn't it? Like the Poincare constant would be like proportional to the variance or something?
Yes,
under,
yes.
under KLS.
So what I was simply saying is that I don't really know whether we can have something really numerically computable for the constant of the KLS conjecture. Of course, I mean, if we have the KLS, if the KLS conjecture is proved, then what appears in this conjecture is operator norm of the covariance operator, right?
Mm-hmm. Yes.
So this is something that we should be able to compute. But then there is a constant in the KLS conjecture.
Yeah. Yeah. Okay.
You may choose not to answer any question for any reason.
Okay.
You may also
All right. Thank you.
at any time.
Okay, great. I guess we're a bit over time, so let's maybe take other questions offline and take a break for the next speaker.
Thank you very much once again.